We've seen how neural networks can learn patterns. But there's a problem. How does the network know whether its prediction is correct? Imagine showing an AI a picture. It says, dog. But how does it know whether that answer is right or wrong? Someone needs to provide the correct answer. And that brings us to one of the most fundamental approaches in machine learning: supervised learning. Imagine we give a machine thousands of examples. But this time, every example comes with an answer. A picture, dog. Another picture, cat. Another, bird. The machine isn't simply looking at data. It's looking at data together with labels. This is called labeled data. And these labeled examples become the foundation of supervised learning. So, what exactly is a label? A label is simply the expected answer associated with an example. A picture might have the label dog. An email might have the label spam. A house might have a label representing its price. The label tells the model what we're trying to predict. Think of it as the answer key attached to each training example. Now we have another important distinction. The information going into the model is called the input, or features. The thing we're trying to predict is the target, or label. Imagine predicting the price of a house. The model might receive information about its size, location, number of rooms, and age. Those are features. The price is the target. So the basic relationship is features go in, a prediction comes out, and the label tells us what the correct answer should be. Think about how a student learns from a teacher. The teacher gives the student a question. The student gives an answer. The teacher says whether that answer is correct. Over time, the student improves. Supervised learning follows a similar idea. The machine receives examples, along with their correct answers. It makes predictions. Those predictions are compared with the labels, and the model learns from its mistakes. Now imagine thousands of labeled examples flowing into a machine learning system. Each example gives the model another opportunity to learn. The model looks for relationships between the input features and the known labels. During training, its internal parameters are adjusted. The goal is to create a model that can take new input and produce a useful prediction. But the model won't get everything right immediately. Imagine we give the model a picture of a dog. The model looks at the image, processes its learned patterns, and predicts cat. Wrong. But now we have something very useful. We know the correct label, dog. So we can compare what the model predicted with what the correct answer actually was. Prediction, cat. Correct answer, dog. The difference between these tells us that the model made a mistake. That mistake can be measured as an error or loss. And this information can be used during training. The model can adjust its internal parameters and try again. This is how feedback becomes part of learning. The basic process is surprisingly simple. The model makes a prediction. We compare that prediction with the known label. We measure the error. Then the training process updates the model. And we repeat. Prediction, compare, error, update. This cycle is repeated again and again. One example isn't enough. The model needs many examples. And it needs to see variation. Different dogs, different cats, different environments, different situations. As training continues, the model adjusts its parameters based on the errors it encounters. Ideally, its predictions become better. But there's another challenge. We don't just want it to perform well on examples it has already seen. One major supervised learning task is called classification. Classification asks, which category does this belong to? Is this a cat, a dog, or a bird? The model learns from examples where the categories are already known. Then, when a new example arrives, it predicts which category it most likely belongs to. Classification is everywhere in modern AI. Another major supervised learning task is regression. Instead of predicting a category, regression predicts a numerical value. For example, given information about a house, the model might predict its price, or given historical measurements, it might predict a future numerical value. So remember, classification asks, which category? Regression asks, what value? These two ideas are worth remembering. Classification produces categories. Cat, dog, spam, not spam. Regression produces numerical values. A price, a temperature, a measurement. Both can be learned from labeled examples. The difference is the kind of prediction we're asking the model to make. Now comes one of the most important parts. Suppose a model performs extremely well on all its training examples. Is it automatically a good model? Not necessarily. What happens when we give it something it has never seen before? That's the real test. A useful model should learn patterns from the training data and apply those patterns to new data. This ability is called generalization. Imagine a student memorizes every answer in a textbook. They get every practice question correct. But then the teacher changes the questions, and suddenly the student struggles. Machine learning models can face a similar problem. A model may perform extremely well on training data while performing poorly on new data. This is called overfitting. The model has learned the training examples too closely instead of learning patterns that generalize. There are actually three possibilities. If the model is too simple, it may fail to learn important patterns. That's called underfitting. If it learns useful patterns and performs well on new data, that's what we want. But if it becomes too focused on the training data, it can overfit. So the goal isn't simply make the model fit the training data. The goal is make the model learn patterns that work beyond the training data. Let's put the entire idea together. Start with labeled data. Train the model. Give it an input. It makes a prediction. Compare that prediction with the known label. Measure the error. Update the model. Repeat. And eventually, we hope the model can take completely new data and make useful predictions. That's the core mental model of supervised learning. But now let's remove something. Remove the labels. No correct answers. No teacher. No answer key. Just data. Can a machine still discover something useful? Can it find groups, patterns, relationships, structure? That's the mystery we'll explore next. Unsupervised learning. And that's where machine learning becomes even more interesting.